All right, good afternoon, everyone. I'm here in place of Nico, who's normally running the seminars. And today we have Dr. Mathias Harzhauser, correct? I said that correctly. And this is really exciting because he is the type of scientist who has the ability to work with the scientific world, the academic world, and he's also connected to the museum world and the public world. And so he has quite a big responsibility of not only doing the kind of research that is very important for advancing knowledge, but he's also one of the people who's bringing that to the rest of the public. And I think that that's something that is really, really important. We talk about that a lot in our program. And it's something that we encourage everyone to do when you have the opportunity to bridge between what you're doing in the laboratory and what you know and helping to bring that out to other people. So now I'll read the formal part. Okay, so I got that. So Mathias Harzhauser is head of the Geological Paleontological Department of the Natural History Museum in Vienna. If anyone's going to the EGU, we might have to stop by there. His research topics include the paleobiogeographic and climatic development of Eurasia over the last 30 million years. The focus is on marine and continental mollusk faunas. And in addition to his numerous scientific publications, he has 12,000 citations, just so you know, and a Wikipedia page. He has published popular science books, curated more than 10 geoscientific exhibitions, and was responsible for the concept of geotainment, which is part of the Fossil Weinviertel in Australia. He is corresponding member of the Austrian Academy of Sciences since 2017, and he was appointed university professor at the University of Graz in 2022, and he's teaching at universities both in Graz and Vienna. And so we're very, very honored to have you speaking to our modest department in Israel, especially during these difficult times. And so enjoy. So if you have questions, anyone who's online, and if you, as he's speaking, you're welcome to send a chat to me in the Zoom, so I can collect questions as we go. We'll try to hold our questions until the end. But of course, you can also ask them yourself. But if you're a little embarrassed and you'd rather have me ask the questions, feel free to send me a chat. Okay, the floor is yours.
Thank you very much for this nice introduction. Yeah, don't be embarrassed because there is no reason for it to ask. But I would prefer to have the questions in the end, because otherwise it will be complex with this Zoom story. Now I'll try to share my screen. Just a second. And ideally, you will now see what I see. So, as you have heard, my specialty is the development of the Mediterranean Sea, of the Paratethys Sea, of the Indian Ocean during the last 30 million years. So it's something that you might be interested as well, because you're sitting at close to the Mediterranean Sea, and it could be quite of interest to understand how this all came into existence. So today I want to give a short overview about things that I'm interested in. Maybe you're interested in them as well. My tool are gastropods. So maybe start with the paleogeographic frame. I'm used to a very dynamic environment, a dynamic planet, because it's changing so quickly. If we jump in here about 25 million years ago, you see Tethys was just split into the Western Tethys part, and in the north you had this huge Paratethys Sea, which was part of this system. And if you move on, in the middle Miocenes, you already have a precursor of the Mediterranean Sea, and still these huge seas in the north with the central Paratethys Sea and the eastern Paratethys. And in the east, you would have the connection to the Indian Ocean. And of course, this is an extremely complex setting, which is forced by geodynamics and by climate. And what we see is a change in the faunas, of course. As soon as climate is changing, as soon as geodynamics is changing, everything is changing there. So this is a perfect past tube of evolution to study. I just moved through some of these maps more. This is a summation of the 12 million years, and about 7 million years, you already had a lake instead of the central Parathetis in the north. And after Mediterranean crisis, salinity crisis, we already have the real Mediterranean Sea, which was reflooded from the Atlantic, and the early Black Sea, and this huge Caspian Sea at that time. So just to get an impression that this is not a stable environment. These seas are changing permanently. And of course, all my organisms within these seas are reacting to these changes. And I was very interested to quantify these changes. So these are biodiversity hotspots, which are forced by climate and geodynamics, with hundreds and hundreds and hundreds of mollusk species there. And the easiest way would be to start to go to literature to collect all this data acquisition. That's easy, and everybody's doing this, and there are online databases where you can simply pull out this information, but you always have to think, bullshit in, bullshit out. So if you just take the literature, then you of course take all the mistakes in it. You have to be very critical with databases, and we wanted to avoid these mistakes in the beginning, so we took the hard road. We decided to make our life as complex as possible, and we wanted to fill in our database only things that have been revised by ourselves. And this means that we started with a critical survey of marine gastropods of this proto-Mediterranean area, and published this one by one in papers, in monographs, and we are still not finished, but now we arrived at nearly 900 species that we have revised very critically. So we really know what we are looking at. And these come from over 110 different sites in a huge area. And then you arrive at some databases. This is just an Excel sheet, but you can put this in an Access database, and then you can really work with it. And we were not only focusing on the taxonomy of these things, we only wanted to have their occurrences, where do they occur. We wanted to know the distribution in a wider sense. Do they occur in the Mediterranean, in the Atlantic, in the Indian Ocean? Of course, we had all the information on stratigraphy. When exactly did these species live? How long did they live? Did they spread, or did they stay very constant in an area? We knew the environment, which is important. Do we only look at shallow water deposits? Are we looking on deep water deposits? So we shouldn't compare things that are not comparable. That's very important if you work with such data. And finally, and this turned out to be very important, we looked also at the protoconch of all these things. Because, as you might know, protoconch of gastropods tells you about the early life of these things. If they had long-lasting planktonic stages where they can spread across large areas, or if they more or less are burst soon after getting out of the egg and crawl around where they were born. So all this information came together, and then we tried to plot this information. Of course, it doesn't make sense to plot such information on a modern geographic map because it's not the same time slice. So we produced maps of several time slices. Here are two of them. This is my area. The left one shows the Langdon optimum. This is the phase when we had the last really very, very warm time in the entire Circum-Mediterranean area. And on the right side, this is the Cerevalian cooling. At the time, it became much cooler. In Antarctica, the first ice sheets started to develop. And then we looked at what did these environment changes do with our faunas. And then we plotted simply diversities. And if you look here, you see we had more than 400 species in the southern basins and slightly less in the northern basins, which is okay, because we know that in the southern basins, we had all the coral reefs. If you have coral reefs, you have a high habitat heterogeneity, which means you have a lot of species. If you go to the north, we lose these reefs because it's too cool already, and it's slightly less. But if you now step in time to this cooling phase, then you see the complete crash of this biodiversity. So more than 2/3 of things disappeared, or even more, which is very, very important. So there are considerable geographic gradients in it, and we had a big collapse of diversities by climate change. And another thing to look at is the connectivity and the gateways between these seas. These blue columns that you see here, these are symbols for oceans like the Indian Ocean, the early Mediterranean Sea, the Paracete Sea, and the Eastern Paracete. And as you can see by the light blue things, you see that have not been always interconnected. There have been only short times when they were connected, and at that time, the animals there could exchange from one to another. And then you can expect in your fossil faunas that suddenly something appears which came from another sea. Otherwise, you have large phases of isolation with no exchange. This means that at that time, you have a chance to get endemic faunas, which evolved only in these areas and had no chance to escape in other regions. And if you compare these data now with extinction rates, this is what we did. We looked in time slices, how many of these species became extinct at a certain level. And then you see that there are some phases with enormous extinction rates throughout this area. And especially if you look here, it's the name that I don't count, but you see here, there are 79% of my marine gastropods disappeared at around 12 million years. And there is a second enormous extinction slightly later with, again, more than 90% of gastropods that disappeared. So what is the reason for this? What was driving these catastrophes? And the first thing is easy. This is climate. At that point where we lost 79% of my gastropods, this is the moment when we moved from the Miocene climatic optimum into the Miocene climatic transition. As I said, this is the phase when ice sheets formed in Antarctica, and in the Mediterranean area it became distinctly cooler. It's not cool that there were the ice bears, but it was cooler, so you lose some of these tropical and highly thermophilic species. And we were able to quantify this by family. And this is just the various gastropod families like trochids or murids, fascicularids and others. And for each family, we looked how many species got lost. And then it turned out there are some which were not much impressed, like the ceratids. Only 20% of these were disappearing. But there are others like the Matildide, the Cariophile, the Brucide, where nearly 100% were lost. And then it's worth to look at how do these animals live, because these families have very, very different life strategies. And then it's quite obvious that those which were hit at most, these are the coral dwelling animals. And that's not surprise, because during this cooling, I already said, all these coral reefs, which were moving far to the north during the optimum, now had to go back. They established again in the Mediterranean Sea, but in the Paracete in the north, all these reefs disappeared. And this means that with the decreasing habitat heterogeneity, I lost loads of my species. And this is just one explanation. And usually it's very difficult to come up only with one explanation for such things, because it's much more complex. And in fact, we traced the second, because it's not just the coral things that disappear. There are other groups, especially those which prefer the deep water. They disappeared as well. What happened? At that time, because the sea level was falling, all the basins became isolated. And this has resulted in a complete change in the ocean circulation systems, which means that we changed from an estuarine to an anti-estuarine system. Before, during this optimum, the bottom water was oxygenated. This means everything could live there. Now, the current system changed completely, and we got dysoxic conditions on the sea bottom, which means that all animals that have to live with oxygen, of course, had problems there, and they disappeared. So this is a second step to explain this amplitude of extinction at that phase. So we lose all the deep water fauna at that time. And then this is just one. If we look to the second big extinction event that we observed, there is now the geodynamics, the driving force, because at that time, at least this Paracete Sea was strongly isolated from the Mediterranean by tectonics. And if to paraphrase the sentence by Bill Clinton, it's not the economy stupid, it's the tectonics stupid. if we want to understand past diversity changes, you always have to mind the climate, but you always have to think on geodynamics. Because if the continents are moving, they change the connectivity of the seas, and this means that immediately this is reflected by extinctions or by endemic evolutions. And that's the case here. The sea was collapsing because it became completely isolated. All the circulation systems disappeared. And we can observe this again from this. If you look at the endemicity in the early Langian during this climatic optimum before the crisis, we had high diversities and low endemicity. And if you move then to the Cerealian cooling, we lose these diversities, and suddenly we became high. The percentages are endemicities, and we see, there is suddenly the endemicity is highly rising in these basins in the north because they became isolated, and now you get isolated evolution there, autochthonous evolution of endemic faunas, which is a nice example that although the faunas generally are collapsing, that some can be the winners because now they can spread instead of the other one which got lost. And again, it's not a unicausal because there are more things involved even in this catastrophe. This is a percentage showing the amount of species that lived in shallow water environments, inner-Neolithic, versus those that we know from the middle and outer Neolithic deep water faunas. And then you can see it through time. We had a maximum during the Langian. It's going a little bit down to Cerealian. And suddenly, if we move up in time during this, what we call summation, suddenly there's a complete loss of these deep water faunas. And again, this has to be explained. And what happened there? Again, we had enormous dysoxia on the bottom water by changing circulation systems. So this is one case. But to explain the magnitude of extinction, we need a second thing. And this was obvious as soon as we looked at the protoconchs. Here you see the measurement of protoconchs during 3 time slices during this optimum phase. And what you can see here is that most of these protoconchs explain that these animals had planktotrophic stages. This means that they lived as larvae in the water surface for quite some long time. So they could spread and were happy larvae in the plankton. But if we look after this crisis, suddenly we lose all these planktotrophic larvae, and there's a big drop down to non-planktotrophic larvae. You can see this immediately in the protoconchs. They are large and have only 1 or 2 rows, whilst the multispiral protoconchs are typical for the planktotrophic larvae. So what happened here? There was some driver that preferred animals that had non-planktotrophic larvae, which lived on the bottom of the shores or wherever, but not in the water surface. So what could be the reason for this? And from modern environments, we know that such changes occur then if you have plankton blooms, phytoplankton blooms. If you get fresh water on the surface water and loads of nutrients coming into the sea, then you get these phytoplankton blooms, and very often the zooplankton doesn't like this. And this is exactly the moment when we lost also our surface water plankton larvae. Another question that I'm very much interested is in immigrations. If you have such a big data set, then you see that at some points there appear animals which are somehow erratics. Here we looked on the mud creepers, on the potamitids, and in some cases you can see that some appeared in the Oligocene, and you can trace them throughout the time, so they have phylogenetic lineages which belong together. But then there are some species which suddenly appear and they have no roots. So they have to come from somewhere else. And these are some of these very, very obvious examples. On the left, there's a strombead, which suddenly appeared around 50 million years, had absolutely no roots. Then this very strange thing in the middle, the Perea, again, is something that is so strange, and you would have recognized if it would have occurred in the Oligocene or early Miocene, but it suddenly arrived, and also the other things. So where did they come from? And now we have to ask, what could be the next areas to come from? Is it the Indian Ocean? Is it West Africa? Is it the Northern European seas? And now we try to find out where are these proto-Mediterranean parotid faunas related to. And we tried, the problem is that you don't have a fossil record from Western Africa and nearly no from the Indian Ocean. So we started another approach. We looked at the modern faunas that you can see here on the left. There are the bioprovinces, and there's a huge database. This is the OBIS database with millions of data points there. And then we looked how many species per family do occur in which area. So you could ask, why are we looking at that? Simply because we think that in each area, each group has its own radiations. That means that the strombids has big radiations in the Indo-Pacific, but nearly none in the West African area. Other groups like some turids had big radiation in West Africa, but none in the Indian Ocean. So this means if you compare them, then they split. And this were looked at the cluster analysis and then on a PCA. And just to show you, these are where the Indian Ocean, Indo-Malayan fauna, the Red Sea faunas plot in this PCA. This is where the European faunas, the Mediterranean faunas plot. And here are where the West African faunas plot. And this means that the West African faunas are dominated by turiclide, by some clavatulids and others. And this is where the parotid and Mediterranean faunas plot. And then it becomes obvious that they are much closer to the West African stuff. This means phylogenetically, they are much closer to this. And this is where we have to look for the precursors of some of these strange animals. And you can compare, this is more or less the same data sheet, and you see some families which are very representative, and you see that the Mediterranean parotid faunas on the left look very similar to their West African modern faunas, where you have loads of clavatulide, of turritellide, of turiclide. And if you compare this with the Indian Ocean, there you have loads of costillariids, of strombids. So these two areas didn't have much in common at that time already, though they were completely separate. This is what we can learn from this. And after the Mediterranean salinity crisis at the late Miocene boundary, we lost even the last of these Tethyan relics. And everything that's then came in at the Mediterranean Sea is, of course, Atlantic in origin. So this is an Atlantic fauna that we are looking at. And if I say that the Indian Ocean and the Proto-Mediterranean Sea were completely sealed off, when did this happen? This happened about 22 million years ago, when the so-called Comforterium land bridge formed. And you may wonder, what is the Comforterium? This is an elephantid. These are animals that evolved in Africa and suddenly appeared in Europe and in Asia, because they migrated from Africa via this land bridge into the northern continents. At that time, there was no connection anymore between Indian Ocean and the Mediterranean Sea. And of course, we can believe this or not. And therefore, we decided, why not go there, have a look in the Indian Ocean at the faunas there. And we did this in big projects and went to Tanzania, to Iran, to Oman, to Sri Lanka, to all these areas, and tried to compare these faunas with those we knew from the Mediterranean Sea. And then we recognized some funny things. It was not the way that things migrated from the Indian Ocean to the west, but even the other way around. You all know probably Tritacna, these huge bivalves. And they started somewhere in the Eocene, in the Atlantic, then moved in the Oligocene to the Western Tethys, managed to jump to Oman, and after the closure of the Comforterium land bridge, they became extinct in the Mediterranean area, but gained foothold in the Indian Ocean, and with the Pliocene, Pleistocene, they started to spread everywhere in the Indo-West Pacific area. So this is a go east scenario, which was a very interesting outcome. And if you once have this idea, you find it everywhere. If you look at Centriscus, this very characteristic shrimpfish, you find the oldest ones here in Europe. Now they are animals in the West Pacific. If you look to the dugong, you find the oldest ones in Europe, and now they're in the Indian Ocean. If you look to the platistinid dolphins, You find the oldest one in Europe, and now they live in the Indian Ocean. So this is a very nice example. And then we looked again at the mollusks and said, how was the influence on the mollusk fauna's disclosure? Before the closure, we can observe that about 30% of the faunas that we find in the Indian Ocean are the same on the species level, like in the Proto-Mediterranean Sea. If I jump in the early Miocene, suddenly I have percentages of very, very few, 0 to 3%. So something big happened here. But still, there are few species that appear on both sides. Here we made the Jaccard coefficient, which tells you about the connectivity of these faunas. And then you see that up to Iran, everything belongs to the Proto-Mediterranean Sea on the left. And on the right, you have these early Indian Ocean faunas. But still, between these blue lines, you see there is some connection with 3, 4, 5 species that appear in both areas. So we were astonished and said, how can it be? If it is completely disconnected, why do these animals occur at both sides? And again, we had to look at the ecology of these things, because the things that live here are typically potamitids. These are the mud creepers. And as we know, these mud creepers can go with birds. So it was easy for them to spread across this Comforterium land bridge, because they simply were going with the birds and could settle the mud flats and coasts in both areas. So you don't need a marine connection to get gastropods transported from one sea to the other. It's something that one always have to keep in mind in these things. And finally, but a question that maybe you could be interested, how old are these Mediterranean faunas? Are they rooted in the things that we've seen now? And of course not. They are not very old, and they are not rooted in these faunas because, as I told you, with the Mediterranean salinity crisis, most of these Tethyan relics became extinct. So when did they occur? And the first one who really was thinking about how we could quantify this was Lyell. Lyell in 1833 had the very clever idea to quantify the stratigraphy horizons according to the percentage of animals that live still today. And he arrived at a percentage of 18% of species that are found in the Miocene strata that are still existing. This is wrong. And why is it wrong? Because the species concept was changing so strongly. Most of the things that Lyell would have accepted as the same species are now known to be completely distinct. But nevertheless, I was interested in quantifying this. And this is a surprise. If you go to, let's say, 20 million years ago, only 1.4% of the fauna that I find here is still living. The same if I go up to in time, still it's lingering around 1.5% of animals, that species that are still living. This is nearly nothing. So the roots of the modern fauna is in the Pliocene and Pleistocene, but not in the Miocene. And interestingly, one could ask, who are the species? What are the species that still survive so long time? And it's interesting that all that belong to this are tonidine gastropods. Maybe you know this, the tonidae are known for huge protocons, which show that they spend enormous long time in the plankton, so they can spread everywhere. And even today, these are cosmopolitan species. No other gastropod species of any other family managed to survive from the Miocene. So there's a big exchange. And this is of interest for people working with molecular phylogenies, because then they can root their species quite clearly. Sorry, my mobile phone is, I have to mute it. Okay. And I'm also working with terrestrial gastropods, and it was interesting to see, is this the same pattern as we see in the terrestrial gastropod faunas? And in fact, what we could show there with the terrestrial gastropods, it's more or less the same. Only in the Pliocene, Pleistocene start the first terrestrial gastropods to appear, which are still existing, whilst in the Miocene, the faunas are completely different. So again, for all people working with molecular data in mollusks, it is very interesting to see that the split of their species had to happen very late in the Pleistocene. And this is more or less where I'm at the end now. And I want to conclude a little bit. This means that The Mediterranean gastropod fauna has roots in Miocene, Pliocene, autochthonous variation in the Eastern Atlantic faunas, so they have nothing to do with Indian Ocean faunas, as was thought for decades and is written in textbooks, but it's simply wrong. That what you see today in the Mediterranean Sea originated basically during the Pliocene Pleistocene. So this is very young. And the same holds true for the Indian Ocean and for the Eastern Atlantic. And the Western relics went extinct during the Messinian salinity crisis. This was the dead end for all the latest survivors of this Tethyan area. And the exchange with this early Indian Ocean east around the Oligocene-Miocene boundary, let's say about 22 million years ago. And again, this is very important for people working with molecular phylogenies, because this gives an anchor point to have the maximum ages for the splitting points of some of their taxa. And this is what I wanted to tell you in short about the things that I do, and I hope you enjoyed it. Now I'm open to questions.
All right. You missed the sound of the applause, but thank you. Thank you so much. It's really, really interesting and obviously very relevant for where we're sitting right now listening to you, since we're on that division between East and West for. So I'll open up for questions. Who would like to ask the first question?
Maybe I want to add one sentence. Of course, the things that I told you now, this is much too much for you. If you're not involved in this, you can't get all this information. But the thing that I wanted to show is that if you start taxonomic revisions on a large scale, you can get out many different answers to different questions. So it's really worth to have a close look in these things. And you are very early in your career, and it simply should show that the world is very open. And that you as earth scientists, you're working with geodynamics, with climate, with evolution of species. There is not much more cool than this. So enjoy
it. Thank you. Who'd like to start with a question? Do I get to start? Well, first of all, I think it's amazing that there's species that there is that 1.5% that is, managed to still exist on a species level for so long. So I don't know if my question is, I'm curious. I don't know quite how to articulate the question, so I'm going to say something that I found interesting that you said, and hopefully there's a question in it. I think the directionality issue is pretty fascinating, because we have a lot of people in our marine school who are working on issues with the species arriving through the Suez Canal. And so here we have this man-made version of a connection that is bringing species from the Indian Ocean species essentially over to the Mediterranean again. From what you've seen from past connections and divisions, are there things that you've observed that seem to control the dominant direction of movement? Like, does it tend to sort of, you talked about east to west, or do the species does a larger percentage go in one direction, or is it sometimes split? Like, how does that look in the fossil record?
This is very difficult to answer, because in many cases we just know one place. As I said, there are immigrations from the Atlantic into this Mediterranean Sea during the Miocene. That's true, and that's fine, but I can't check it in the Atlantic because there are no fossil records there, and there are no sediments to check. So this remains very vague. In the moments where we see, for example, the immigration from the eastern Parodontis in the central Parodontis, if you have a fauna which is highly adapted to certain environmental conditions, then it will outcompete everybody else. That's very obvious. But if you have a very healthy system, then it's very difficult to get into it, and only few species manage to get foothold there. And On the other hand, I think, but it's just my opinion and not science, that the success of the Indian Ocean taxa is that they come from an ecosystem which are much more elaborate and tight and more competitive than the comparatively poor Mediterranean system. So it's easier to get foothold there. Other way around is much more difficult. Very few Mediterranean species manage to get foothold in the Indian Ocean. There are some, but they are not so much. So I think it's the complexity of the system which makes you more fit. But it's an opinion. Biologists may have another opinion.
So you equate complexity with health for a system?
Did you hear the question? The question is, would you consider complexity to be synonymous with healthy in a?
Yeah, don't mind my language. Complexity would be scientific, but health is not scientific. With complexity, I mean the amount of interactions between the heterogeneity between the microhabitats, probably. So in a system with lots of coral reefs, you will have more of this than in the Mediterranean Sea, where you lack this. But this is not my field of expertise, so don't take me too serious in this.
Any live questions? I have some anonymous chat questions. Okay, one of the questions that I got, they asked whether the cosmopolitan species that you described, has it been possible to reconstruct their environmental range? Like, are they highly tolerant of different environments, or?
No, that's not. These are, some of them are exclusively shallow water species, some are deep water species, but that's not the point for them. The point for these species is that they have so long planktotrophic stages. So they spend more life as a plankton than as a benthic organism. And this makes them very widespread. Like microplankton is widespread and cosmopolitan. And that's their trick. And there's only this family within the gastropods that has this very long stage of duration as plankton. So it's not the adaptation to wide ranges of ecology. There would be others that would fit much better in this. Mm-hmm. It's their ability to spread.
Anyone? Ravita?
I have a question about the seawater composition or the dissolved salts. Where this inner seas saltier or fresher compared to the open ocean?
Did you hear the question?
Mm-hmm. Yes, they both. Of course, it's a matter of precipitation. As soon as you close off such a system, more or less, then if it's a dry system, you have more evaporation, then it will get alkaline and saline. We had this in about 12 million years ago. The Sarmatian Sea was like the Persian Gulf. You have oolite formation, and it was really highly alkaline. And 1 million years ago, 2 million years ago, the precipitation was higher than evaporation, so you got a lot of fresh water, especially on the surface water of the sea. This, of course, lowers the salinity a bit. And if you have loads of fresh water on the surface of the sea, it means that the plankton is usually damaged, because zooplankton doesn't like this, whilst the phytoplankton loves it. So the one loves it, the other one collapses. So you have both, and this makes it so complex, because you have to understand this before you can work with your faunas. Otherwise, you will go in circles.
Who else? Okay, I think we have one final question here. Thank you so much for this really, really wonderful talk, and I hope everyone also paid attention to the figures in the presentation and how direct and clean and clear, you know, how you can take these big concepts and be able to really show them nicely, which of course he has much experience in this. But the last question here is, if you had unlimited funds Where and you knew that you would be able to find the fossil record. What is your dream place to be able to gain the fossil record for this kind of study?
I'm too rationalistic for such questions. Where I would like to go further is Southern Africa. I want you to just go to the Andaman Sea, the Thailand area. This is my terra incognita, where still things have to be found. West Africa would of course be cool, but we know that there is no sediment. So the funding doesn't help if
you know too much. Yeah.
Yeah.
Wonderful.
Step by step, we will do all these things if we live long enough. Okay.
Well, thank you for a wonderful talk. And
yeah, I say thank you for inviting me. Hope we will have more, please. Thank you very much. Yeah. Goodbye from me.
And I will if you'd like, Nico will add you onto our mailing list because I'm sure you don't get any emails. So you need to get some emails sometimes. So if you want to listen in on some of our seminars, or you can, delete it. But you're welcome to join us. We would be happy to have you.
Goodbye.
Bye-bye. Bye.